Hi, and welcome to a video on the comparison tests for a calculus course where we are given an infinite series and we are trying to determine if that infinite series will have a convergent sum or if that infinite series will just have a sum that continues to grow forever and ever and is divergent. Again, we're not trying to say what that sum of that series is going to be. We can have some decent approximations, but we're not going to say exactly unless it's geometric or telescoping. So those were sort of the two basic tests that we started this whole unit or this idea of series with. Was if a series is geometric, we can know pretty quickly whether it will converge or diverge as a sum. And if the series is a p-series, also I can look at it and do one quick little look sort of test and determine if that series would converge or diverge. So hence we need this comparison test. There are two comparison tests. There is what I will call a direct comparison test where you're going to look at inequalities, and then there's a limit comparison test. And I do think that in my experience, I've been teaching calculus for about 20 years now. In my experience so far, students have preferred the limit comparison test because by now doing a limit is pretty quick for you. But let me just show you what the direct comparison test shows first. So let's say that you have some known series, and I'm just going to graph it. It looks like so. And we're going to call that series B sub n. And we know this series, we're going to say this one converges, okay? Let's say I did the geometric series test. My common ratio was 1/3. That's less than 1, so I know that series converges. I'm just making it up. All right. So if that's the case, and I tell you that we have another given series down here, A sub n, which is just below B sub n. Well, if A sub n is always below B sub n, and I know that B sub n has some convergent sum, right? I know that it converges to some value. That's finite. So something less than finite also has to be finite. Again, I'm not trying to determine what that is. I'm just trying to say whether it will be finite or infinite. So I know A sub n has to also converge. So on the flip side of that, right, so I can use that inequality to sort of help me out. So on the flip side of that, if I know that I have the same series, I'm going to call this B sub n, but now I know that this series diverges. Maybe it's, 1 over n. Maybe it's the harmonic series, for example. And I have another series not below it, but now above it all the time. So A sub n is now always greater than B sub n. Well, if B sub n as a series is infinitely large, and I know I have something greater than that, then it has to also be infinitely large. So that's all in essence that the direct comparison test is trying to show. But you have to have something to compare it to, and you have to know what that series will do. So you are kind of doing two tests in one. So because of that, when you compare, I want you to really compare to something that doesn't take too much thought. So our geometric series, we've had lots of practice with. We probably are very familiar with that. P series, again, it just has to be set up for that. Or maybe it's harmonic or some type of other easier series. I would not necessarily compare to an integral test, for example. I'm not suggesting that you can't. I'm just suggesting that's not necessarily what the comparison test was designed to help you with. So I did write this box here of what the actual direct comparison test will look like, but I'd like to just jump right into some of these examples and get you started so you can see how this is going to look here. So determine whether the series will converge or diverge. Okay, I have the series, it's obviously infinite from 1 to infinity, 5 over 3 plus 2 to the n. If I think about at infinity, what's the least impactful part of this whole thing? It's that 3 plus. So what I'd like to do is I'd like to compare this to this series right here from 1 to infinity. I don't necessarily want to change that aspect of it, but I'm going to compare it to 5 over 2 to the n. Okay, and we're going to see what that series will do. Because I think at infinity, it's probably going to behave close to that series does if I just sort of ignore temporarily that 3 plus. Also, what happens is if you ignore the multiple terms, now again, I'm really only focused on the highest powered term, right, of that denominator. So if I ignore that other term of that plus 3, what happens is now I only have one ratio here that I'm looking at. So the chance that it's p-series or geometric is much higher. So I'm going to write out the first few terms here. I have 5 over 2 plus 5 over 2 squared. That does not look like a 2. Plus 5 over 2 cubed, dot, dot, dot. It shouldn't take me too long to figure out that this is a geometric series. And my common ratio is 1/2. Since that ratio is less than 1, therefore it converges. Remember that? That was from our geometric series section. Now, that does not automatically mean that my series that I started with converged. I'm going to put this in green just so I can always talk about the green series versus maybe the yellow series, okay? So just because I know that yellow series converges doesn't mean I know what that green series does. So I showed you this graph before. If you think of this looking like so, and you know this converges, you want your series to be less than that because again, this is finite. So what I'm going to try to show is that this green series right here is less than or equal to, because perhaps I just did a whole bunch of nothing and maybe they are the same series, which they're not, but sometimes that'll happen to you. So I just want to show that the green series is less than or equal to that yellow series. And because my n is always going to be some whole number, so it's always positive, it's always whole, we kind of get away with some algebra that before we might not have with inequalities, but I will multiply both sides, or some of you like to think of it as cross multiplying, and that is fine. However you see fit here, you should end up with this. Again, I multiplied both sides by a common denominator, which was 2 to the n times the quantity 3 plus 2 to the n, and you'll get the same place. And then I can distribute. So that's 15 plus 5 times 2 to the n, which is not 10 to the n. I can subtract 5 times 2 to the n. So I get 0 is less than or equal to 15. And because this is a true statement all the time, or because it's at least a true statement for all positive n values, I can say my series will also converge. And I would say I like to call it the direct comparison test, or you can say DCT, direct comparison test. The only reason I say direct comparison test is because then you'll have coming soon the limit comparison test. And so I just like to know, did you show the inequality or did you show that limit? All right, so let's look at another one here. So one thing that happens is we try to make, you know, that old saying, what is it, try to fit a circle into a square or something like that, and it's just not going to work. So what I know is that, again, I'm looking at this green series right here, and I'm going to temporarily compare it to this yellow series. And all I did in this case was take out that 1 plus, because again, at infinity, I don't know, that may or may not be the most important part of that problem, right? So if we do that, this is actually a p series because this is n to the half, and so p is less than 1, so I know that series will diverge. And so what I think is if my series will diverge, I want my given green series to be bigger than that. Because if I already know that this sum, for example, is infinitely large, I want my series to be bigger than that because then I'll know that it's also infinitely large sum. But take a look at what happens when we actually try to solve that inequality. So I did put the greater than or equal to. So I'm saying I want my green series, right, to be bigger or equal to than that known series that diverges. And when we multiply both sides and we try to solve this, I get 0 is greater than or equal to 1. And this is where some people get desperate and they say, no, I must have done something else wrong. I'll just change the inequality. No. Or they say, oh, okay, well, that was false. So this yellow series diverged, and because I got false, that must mean this one converges. No. So again, if you look outside your window and you say, you know what, it is not raining right now, that does not mean that it's sunny. It could just be cloudy, right? So you can't jump from A to Z without kind of going through all of the steps in between, so to speak. You can't just jump to the automatic opposite thing. You are trying to show that your series diverged, and that's the closest series to the green series, and so we probably think it should diverge. So what happens is, all that means is that you need to compare to a different series. So if you want to keep using the direct comparison test, just pick a different series that still does what you thought initially. We thought we diverged. So I'm going to pick another series kind of close to this one, kind of close to 1 over n to the half, that also diverges. So in this case, I picked a new yellow series here to converge to, which was 1 over n, the harmonic series, which also still diverges. And when I look at that inequality will be true. Again, I get a quadratic. And so when I look at that, yes, as n approaches infinity, that will always be greater than or equal to 0. So yes, this will also diverge. Your other option is, because you got sort of a failed test the first time you did it, right? That failed. That was false. You could just say, you know what? I'm going to use instead the limit comparison test and see if that leads you to a better result. Okay, I'll teach you limit comparison test and a few other examples. So you have two choices. If your first series that you compared it to didn't work, well, then you can change your test or you can change your series. Doesn't matter, but you got to change something. Okay, so let's go through another example here and see if this is going to work. So again, I'm going to look at my series here, which I'll call this green series, and I want to find sort of a yellow series, if you will, to compare it to. And just for our notes' sake, I'm going to say I'm going to compare to, just so you can see that later too when you look, from 1 to infinity. And again, if you think about at infinity, what is the least meaningful of this whole problem, that plus 7 is not as meaningful as 3 to the n or 5 to the n. I get rid of any term except for maybe the highest powered term on each numerator or denominator, or my exponential part of that function. All right, so if I write this out, this becomes 3 over 5 plus n is 2. It'd be 3 squared over 5 squared. When n is 3, 3 cubed over 5 cubed, dot, dot, dot. Most of us have probably figured out by now that this one is geometric. All right, so this is a geometric series by definition. And so I look and say my common ratio is 3/5, which is less than 1. So I know that this yellow series that I'm comparing it to will converge. So again, now I go back because you haven't done a comparison test yet. All you've done is the geometric series on some other random series. Well, this is where the comparison part comes in. So I'm going to take this green series that I know I want to find what does this series do. If I know the yellow one converges, I know I want to be less than or equal to the series that converges. Again, converges is representing some finite value. So if it's finite, I want to be less than finite, and I know I'm going to be some finite value as well. So again, you can multiply both sides, however you kind of see this. It will be 3 to the n times 5 to the n, and 3 to the n times the quantity, 5 to the n plus 7. And I'll keep going here. I can distribute this. I recognize that I can multiply that, but don't worry, because you're going to subtract it from both sides. So if you see I have 3 to the n times 5 to the n on both sides, I can subtract that. That adds to 0. And so I have 0. So 0 is less than or equal to 3 to the n times 7. You can divide both sides by 7. 0 is less than or equal to 3 to the n. Well, sure, n is greater than or equal to 1, right? n started at 1 and goes to infinity and continues to be positive and whole throughout. So yes, this is an exponential growth function, 3 to the n. So yes, that will always be greater than or equal to 0. So I can stop there and say true. Therefore, by the direct comparison test, so you can write it out, or you can call it DCT, whatever you want, whatever's going to make sense to you later, my green series will also converge. What I find is that when students ask me questions about this section, or when they have difficulty with this section, they don't have any of that stuff written down. They look at it and they say, oh, it's geometric, so it converges. Okay, but where is the comparison test part of it? Because sometimes you might get tricked and it might not do what you actually think it does. So we have to show that it is doing what we think it is doing. Okay, so just a couple more here before we get to the limit comparison test. So if I look at this one right here, I suggest, and this is a personal preference, I suggest keeping coefficients. So when I look at this and I say, what am I going to compare this to? I'm going to compare this to the function where at n approaching infinity, those terms wouldn't necessarily matter. Meaning, I know what this graph looks like based on 5 over 2n squared at infinity, n behavior. So none of this plus 4n plus 3 is n behavior stuff. So I'm going to compare to the series from n equals 1 to infinity of 5 over 2n squared. And just trust me that you could certainly compare this to 1 over n squared and just look at your overall powers. But I really think keeping coefficients in here is going to help you long term, especially when we get later on to ratio test and root test and all of that. I just like to keep coefficients so I can show what I'm trying to show. So the series that I'm comparing it to, right, this is I've been highlighting these yellow all along. I want to figure out what this series does before I go any further. My base changes every term, so this was our P series by definition. And P in this case, the exponent on that power, or the exponent on that n, is 2, which is greater than 1. And so if you remember from P series, when that P is greater than 1, this series will converge. Okay? So I think now, looking back at this green series, I think if I had to make an educated guess that it will also converge. But I want to make sure that this green series is less than or equal to this series. And you can also not just look at it and say, oh yeah, sure, that's the case. Nope, you have to actually get all the way down to a true statement regardless of polynomial like this, or regardless of n. So I'm going to multiply both sides by your common denominator. Again, some of you think of it as cross multiplying. It works as well. All right, and then I'm going to distribute. So I have 10n squared on the left. That didn't really need distributing, but the right side does. 20n plus 15. And you want to get this to a true statement where you don't even have to think about it truly, where anyone would be able to look at it and say, yeah, well, of course that's true. Okay, so I'll subtract 10n squared from both sides, so make sure you put that 0 there. 20n plus 15. I'll subtract the 15 so I can solve for n. And if you divide both sides by 20, this would be negative 3/4. So is n greater than or equal to 3/4 for the whole problem? Well, yeah, n starts at 1 and goes to infinity. So that is true all the time. So my series will also converge. Okay. So one last one that I just wanted to look at. Again, you can certainly get the problem, write it down, try it, pause the video, and then return in a second here for the answer. This one, I'm going to, first of all, rewrite this k cubed plus 4k plus 3 here, all to the 1/2, so I can see it as an exponent. And then what I'm also going to talk about is this plus 4k plus 3 again is not as dominant as that k cubed, but it is underneath the square root. So that function is k to the 3/2, not k cubed. You've got to make sure you keep it under that square root. Okay? So when I'm comparing this, it's not always the first term, remember. I'm talking about the highest powered term or the most dominating. So I'm going to compare this to k to the 3rd over k to the 3/2, which really is 1 over k to the 7/6. Again, I want it in p-series form, so I want 1 over n or k or whatever to a number. My base is the term number, and my exponent is what is staying consistent in this case. My exponent is 7/6, which is greater than 1. So I know that series converges, so I wanted my green series, right, to be less than the known convergent series. And so when we do that and we take our green series and make it less than or equal to my yellow one, you're just looking for a true statement or an identity that is true all the time. And after you multiply both sides, I can square both sides. And that becomes very helpful because, again, all my values are positive anyway, so squaring them is just making them larger and more positive. It's fine. So I don't have any domain restrictions because k to the 3/2, remember you can't take the square root of a negative number. I don't have negative values for k. So I'm not, adding too many values to my domain that I didn't already want. So then I continue solving, and k is greater than or equal to that negative 3/4, so yes, it does the same thing that I thought it did. All right, so let's talk about that limit comparison test now. And I do think that many of you will choose the limit comparison test over the direct comparison test because of the inequality involved in the direct comparison test. This starts the same though, so it's going to look and feel exactly the same. The only difference is instead of that inequality that you would be doing, you're going to be doing a limit. So I'm going to say right from the beginning, again, this is going to look the same. Identify what do I want to compare this to. I'm going to try to compare it to something that is geometric or p-series or something harmonic, something that doesn't take me all that long to figure out what it does. And I'm going to compare it to 1 over 4n squared. Again, I keep coefficients. That is entirely up to you if you choose not to. So 1 over 4n squared, what does that do? Well, my exponent is staying the same. That's the p-series, where p is 2, which is greater than 1, which means that that is going to converge. So I have an option here. If I want to use the direct comparison test, I would be saying again that my given series, the green, would be less than or equal to that yellow. Or you can choose the limit comparison test. And the limit comparison test means you're going to say limit, obviously, as n approaches infinity of the ratio. Your green series, so your series that you want to talk about, right? You're trying to determine what it does, over the yellow known series. And so I'll rewrite this because most of the times when you're dividing by a fraction, this should make sense to you right from the beginning, that I'm going to look at my green series times the reciprocal of my yellow series. So I'm going to color code these here. Green, green, yellow, yellow. So whether you look at it as division or the multiplication, again, most people are going to go straight to multiplication, especially after we do the ratio test, because we're going to do limits with there as well. So we have to identify this limit. Well, again, think about L'Hopital's rule, or you can think about Calc 1, 4n squared over that 4n squared. This limit is going to be 1. As long as the limit is not 0, I know that it'll do the same thing that the other series did. And so by the limit comparison test, I know that my green series will also converge. So again, many people like that limit option better than the inequality. So let's do it again. So here is one where I have the sum, and again, I'm going to color code this one green. My original will be green. And you have to identify what do you want to compare it to. So I want to compare this to the sum from 1 to infinity. Again, I'm going to keep coefficients, but you don't have to. So of n squared, for example, over 2n to the 5th would be my highest power terms. So I'm going to compare this to 1 over 2n cubed. And you need to state, what is this? Well, this is P series. P is 3, which is greater than 1. So I know that this series will converge. And so now all I have to do is make sure that this ratio, when I do the limit as n approaches infinity of my green, 2n to the 5th, right, your series that you want to determine what is happening to this series, is it converging or diverging, times, and I'll just reciprocate, because instead of dividing, I'm going to reciprocate the yellow, what I'm comparing it to. So I'm going to say times 2n cubed over 1. Well, if I look at this limit is also 1. So if I look at it, the limit of green over yellow is not 0. So therefore, it will converge also. And I would just say by limit comparison test, or LCT. You can certainly write that out if you choose. So it's nice because we want any limit other than 0. Then they both will converge or both will diverge. Okay? All right, so here's one where we're going to have to do a little bit of work with the limit, and we are almost done. So let's look at what we want to compare this series to. If you are kind of bored at this point, I would highly recommend pause your video. You know, we're 30 minutes in. You probably fully are aware of comparison test by now. And let's see what we're going to compare this one to. So we are going to compare this one to 1 over 2 to the n. So I would say pause the video, try to do it, and then restart the video and see how you did. So this one is geometric, right? Because my exponent is changing, not my base. And my rate is a half. And since my rate is less than 1, I know this converges. And so all I want to figure out is my limit, right, as n approaches infinity of this series. I just want it to be kind of some finite number, not 0. So my limit of the green, right, my given series, I'm going to multiply by the reciprocal instead of dividing by my comparative series here. And this limit is infinity over infinity. You do not get to say that that limit is 1 yet. It's not. It's infinity over infinity. So I get to use good old-fashioned L'Hopital's rule. So limit as n approaches infinity. L'Hopital's rule comes up all the time in Calc 2. So here we go. Limit as n approaches infinity of derivative of the numerator. Derivative of 2 to the n is 2 to the n times natural log of 2 over derivative of that denominator is derivative of 2 to the n, we just said was 2 to the n natural log of 2. Minus 1 would be 0, so I don't have to write that. So no plus 0, and that's it. Now, before you look at evaluating the limit, look at your algebra. Natural log of 2 divided by natural log of 2 is 1. 2 to the n divided by 2 to the n is 1, algebraically. So I really have limit as n approaches infinity of 1, which I know to be 1. So I'm good. So I say it also converges by limit comparison test, or LCT. If you get stuck, you can look at, if the limit comparison test isn't working for you, you can look at just sticking with the direct comparison test, but there certainly are reasons for both. Otherwise, we wouldn't have taken the time to cover them. And I'll just leave you with one extra example, only because most of the ones that we talked about I realized converged. So here's an example showing one where we compare it to a p-series. So here's my comparative series, and that series diverges. And so when I look at my given series that I'm trying to determine what it does, my limit again is 1, and so it will also diverge. So this does show both divergence and convergence for both limit comparison test and direct comparison test. I hope you find this helpful. Thanks for watching.